Thanks for the introduction. So, as mentioned, my name is Greg Haynes. I'm a software engineer at IBM. I've focused primarily on open source and cloud software development. Recently, this has meant focusing on Knative and, as mentioned, the cold start performance characteristics of Knative. And so my hope here today is to give you all a bit of a story of what we've worked on over the past 6 months in trying to improve Knative's cold start performance. The idea being it's a good story from a user standpoint on how you can potentially beat many of the performance characteristics you get from Kubernetes out of the box. Because in Knative, performance in this scenario, when we're scaling from zero, is extremely critical to the usability of our platform. In addition to that, I'm going to talk a bit about the different measuring techniques we've used to find where in Kubernetes this latency has been introduced, and different methods people can use to debug and diagnose performance issues in Kubernetes. So how we're going to get there. I'm going to start with a bit of Knative design, and specifically our architecture for what goes on during scale from zero, just to give some context about the things I'm discussing later on. Then there's going to be a lot of discussion about investigative techniques and specifically how we can get tracing spans that are meaningful and detailed analysis about what's going on when we're mutating Kubernetes resources. Then through that process, we're also going to look at how we can, given this information we get from these spans, how we can use that information to find some maybe novel techniques or some clever solutions to beat the performance characteristics we're seeing. And lastly, but most importantly, we're hoping to actually get a result out of this, which is faster cold start performance. So why is this an issue for us? If you think about a normal application, maybe you're running a blog on Kubernetes or something like that. The SLOs of the Kubernetes control plane generally are not affecting your application, right? So pod startup time hopefully is not going to affect the response time of your web application on Kubernetes. If it does, there's something terrifying probably going on there. And that's great. It's a great design goal, and it's something everyone should achieve. And again, it's almost certainly recommended and to be avoided at all costs to put this Kubernetes control plane within your application's data plane, and therefore take on the SLOs of the Kubernetes control plane as part of your application's performance. But here in Knative, what we're trying to do is actually extend Kubernetes. So our application, to an extent, is Kubernetes itself, and therefore it's somewhat unavoidable that the Kubernetes control plane's SLOs dictate our application's SLOs. We are essentially the platform. And so we can't completely avoid this. And if we even were to try and avoid this, this would essentially mean that we're reinventing everything below us, which is intentionally not a design goal. So these SLO characteristics are extremely important to Knative's performance, and it's somewhat unavoidable. Now, that being said, not everyone is building a Kubernetes, and I understand it's not always generally applicable, but many of the things we've discovered, maybe there are certain areas, such as maybe you're running test infrastructure, where performance of your test deployments are going to be very dictative of how easy your test infrastructure is to use. Or in other words, generally performance is something that people can always enjoy, whether or not it's a strong requirement. And the problem, to state it again, is that cold starts in Knative are costly. To give you some context, when we began hacking on this, without Istio, about 5 to 6 seconds. What this means, to give some more context about cold start, we're a serverless platform. So your application, we allow it to scale to zero, meaning your application's getting no work, no requests, no one's trying to use it. It's great. You're not paying for that infrastructure cost at that point. We stop running it entirely. But then when you get another request later on, we have to start your application. So we have to pay the cost associated with deploying and getting your application up and running. And in Kubernetes, this means starting a pod, creating a service, or populating a service's endpoint so that networking traffic can reach that pod. And this is somewhat costly. As mentioned in the previous talk, I believe the target SLO for pod startup in Kubernetes is 99th percentile, needs to be below 5-second response time for pod startup, which for cold start, that is significant. An interesting data point, GitHub webhooks, for example, generally time out at about 5 seconds. So if your cold start is above that, that's completely limiting that use case for us. So it's important that there's certain targets we're able to hit to provide more use cases. And even better than that, if we can get below 1 second, that's when many applications are able to be used on our platform and present cold start more forward in their interface. And then if you can get down to a couple hundred milliseconds, at that point, you maybe are able to do user-facing applications, which are able to undergo cold start. That's where we hope to get to. We have a long way to go. So a bit about our architecture and how this works. When a request comes in and your application has scaled to 0, so we're no longer running it, we have this pod called an activator. And it's just a deployment, nothing terribly special there. And we reroute all networking traffic to go to this activator service. The idea being your application's not running at this point. Your request can't really just float out in the ether and not go somewhere. Something has to handle that request and hold on to it while we spin up a pod or your application to serve it. That's the activator's job. From there, the activator knows it got a request for your application. It pokes what's called our autoscaler, which, as the name implies, is responsible for controlling the size of your deployment. The autoscaler says, oh, I have a request in. I need to set at least a scale of 1. It creates that initial application. The autoscaler does this by talking to Kubernetes, and it literally sets the replica count on a deployment to 1, which goes and creates a pod, which goes and populates an endpoint. And eventually, at the end of this, the activator notices this and says, OK, I can now forward the request onto your application, and does so. It's a roughly 4-step process. It's not terribly complicated, but the end result is activator sees your application start, your request gets forwarded through. And as I stated before, we have about this 5 to 7 second cold start time base. The first question is, well, where is that time getting spent, obviously? So one of the nice things we're able to do in Kubernetes is build off of Istio. The idea being that then we get its observability characteristics for free. So I've highlighted in green here the request path of a request coming in externally. And so it goes, as I mentioned, to the activator, which then forwards it to your application. Istio should be giving us tracing spans for those things immediately, and we can see if anything odd is up. And that's what this is. You're going to be seeing a lot of these traces throughout this talk, because this is really the main debugging tool we've been using to figure out where time is spent and see our improvements. If you're not familiar with this interface, this is a Zipkin's UI. And essentially, these are just spans, tracing spans around different operations that occur. The top span, which is that blue line you're seeing, is the activator. So when the request comes into the activator, that span begins, and when that activator responds, it closes the span. And I've labeled it at the beginning, that's the request initially coming in. And then we see a whole lot of nothing, essentially, until we get endpoint ready. And that's when our activator begins trying to send a request to the user application. And fairly shortly afterwards, we see that the request was served. So we got some information here, but to be perfectly honest, it's not terribly useful. We have this giant block in the middle of we're waiting on something before our endpoint becomes ready. And this is one of the major issues we ran into initially. Even using Istio, there's a lot of context missing. The reason being, as I mentioned, our activator talks to an autoscaler, which talks to Kubernetes, which manages a set of resources, which then creates our user application. Those things aren't tied with the request lifecycle, right? Our activator talking out autoscaler is not necessarily one-to-one with a request. We could have multiple requests come in and want to scale up a pod to 1 initially. Same with Kubernetes resources. There's no really notion of a pod is tied to this initial request that came in. There's no way Istio can know about that. And it's a bit of a problem because there's not a great solution to this problem, I guess I would say. But what we've done, for now at least, is we've set up a set of informers inside of our activator, which watches these Kubernetes resources. So we set up essentially application-level spans that watch the various Kubernetes resources we know are going to get created as part of this cold start. So an example being maybe you have a Hello World application. We know we're going to create a Hello World pod with certain labels on it. So we set up informers to watch for those. And then we have a state machine watching. Here's when the pod started. Here's when it's running. Here's when it became ready. Hopefully this gives us telling us a story about what's going on behind the scenes when this activating request comes in. And as mentioned on the slide here, I really wish I had a better solution for this. One of the issues being, as I'm describing, it's a state machine that we've made that's tracking resources and trying to map them to a request. It's not a one-to-one mapping. It's fairly fragile and not great. So if there's a better pattern for this, I would love, please come talk to me. I'd love to hear about it. So doing this, though, we're able to get a little bit more information. Most notably, we have a new span now that shows our pods running. It gives us basically 7 seconds of our pod. We're waiting for our pod from when it starts to when it goes ready. That in itself isn't earth-shattering. We just know we're waiting on a pod, but it's something. Fortunately, we did a little bit more than that. We also added tracing spans for our container life cycles as part of that. So when each individual container in that pod goes from started to ready to running to ready. And that's when things get interesting. We're able to see right away that there's a 4-second container called istio init. Right? In hindsight, it's a little bit obvious. If you know how Istio works, one of the things it has to do is IP tables programming of your pod as it starts up, so it can reroute all outbound traffic through its proxy. Well, init containers, it does this via an init container that runs some IP tables programming rules. Init containers, by definition, run before your containers of your pod start. So just off the bat, this means they have to happen in sequence. And there's always a base startup cost with an operation like starting container. In my experience, it's roughly 2 seconds, depending on container backend and performance. But you're paying that startup cost twice now, all of a sudden. Right? So you've doubled the pod startup time, essentially, simply by using this init container. That being said, it's not necessarily an Istio problem, but this needs to be gotten rid of. You can't run it with an init container if you're looking for sub-second pod startup time. So fortunately, Knative doesn't necessarily hard depend on Istio, at least everywhere. We can just simply run without the sidecar on users' applications and still use it elsewhere. But also, for folks who are very interested in using it, there's some alternatives. Specifically, there's a CNI adapter that Istio supports. It's a little bit out of the scope of this talk, but I think there's a talk fairly shortly afterwards called Istio on Knative, where they talk about this a bit. But at the end result being, we have to get rid of this init container. And in doing so, things open up a lot more, right? We start to see now, pod startup time is about 3.2 seconds in this new trace after we've removed this init container. So we've halved it right there. That's a significant low-hanging fruit improvement. But there's also an additional gap we're starting to notice. What's going on here is the overall startup time has decreased significantly. Like I said, we halved our pod startup time, which has scaled everything out. And now we notice that before our pod starts, there's this large time gap that I've circled here. And it's not really clear what it is, but it turns out that having this level of observability is great for finding regressions in your application. And it turns out we had redesigned how our autoscaler and our activator work a little bit, and specifically the stats components. And they were driving it by pulling loops that take 1 to 2 seconds each, which is a 3-second delay before we even attempt to start up a pod. So there you go. I guess the key thing to keep coming back to is that observability and metrics are great for a reason. That being out of the way, those two low-hanging pieces of fruit being fixed, we get a much better, we're starting to look a lot better here. We see now pod startup time in this graph is 2 seconds. That's because there's some variance in it due to several components. But overall startup time is now a 2.5 second window. So it's a long shot from where we began. And more than that, the low-hanging fruit seems to mostly be gone here, right? Like what we're seeing is a pod. Most of the things that we're waiting on are two containers starting up. Pod creation time takes most of our blocking time, and our request time at the end takes a little bit. So we're going to have to dig a little bit further to figure out some ways we can potentially optimize this a bit more. One thing you don't see here is we actually added additional metadata to each of these traces. So I've described we have a state machine recording when each of the containers in a pod go starting, running, and ready. And you can think of these phases as started is when essentially the CRI sandbox create call happens. So that's, you said create a pod. It's trying to create the environment in which to run that pod. Running is essentially when the CRI container run gets called. So we've exec'd your program, and it's starting to run, and then ready is dependent on Kubernetes readiness probes if you have them defined. So it's whenever your application reports that it's healthy. And you can't see them in these traces, so I've labeled them for you. We actually have it as part of our Zipkin trace metadata. And one thing we notice when you look at this is that the application under test here is just a hello world go. It's a hello world go binary that opens up port 8080 and returns hello world go. It really has no business taking a second to start up. And the end result of that is we find that Kubernetes readiness probes have a minimum granularity of about a second. And that's just the value used to define readiness probes are a second. Are second based. You can't get smaller than that. So it's sort of a hard stop, and we have to get clever here. And so we came up with this trick where we're doing it's long polling of these readiness probes, essentially. So if you know a bit about how Knative works, we have a separate container in everyone's application called the kubeproxy. But it's our container where we can do Knative things, essentially. And what we do is we define a readiness probe from Kubernetes into this kubeproxy, and we don't allow users to define readiness probes on their pod. In fact, what we do is we undefine them on a user's pod and define them and perform those readiness probes from our own kubeproxy. The idea being is we can then control when a Kubernetes readiness probe hits our kubeproxy, we're going to leave that connection open. We're not actually going to return unhealthy if it's unhealthy. We're just going to wait. And then we're going to poll extremely frequently on our user application. So hopefully, eventually, if that user application returns that it's healthy, we can then immediately return back on that Kubernetes readiness probe, which performs essentially an edge trigger to kubelet that it should update the status of that pod. And result being, as soon as our user app goes ready, hopefully we can get a almost immediate ready status on our pod. Unfortunately, after implementing this, we still are seeing this 1 second delay. That trace I showed you before is from a version of our code where we implemented this long polling. And what we found out is that although our solution works to an extent, it's really only setting an upper bound of 1 second because kubelet and our kubeproxy code can race starting up. So essentially, our kubeproxy is not necessarily started by the time kubelet sends that first probe in, and there's nothing we can do about that. It's going to get a TCP reset at that point, and we have to wait the full second until the next probe comes in. But still, the reason I mention this is because for most applications, sub-second startup isn't a thing. But maybe you do want to have more accurate readiness probe response, and this whole concept of long polling a readiness probe is a fairly neat trick, I think, to get accurate transition times for when your pods go ready. Similarly, as a plan to mitigate this, you can do what's called an exec probe instead of a network probe, which in theory doesn't have this problem because the execs aren't waiting on a socket to become available. But that's still work to be done. So let's step back a bit here. And we'll side table that and say, look, we got upper bound of a second on readiness probing. Maybe there's not a whole lot we can do there off the shelf. But let's look on the side here. We also have this Dataplane delay that's going on. And if you notice a little bit, or if you notice what's happening, we have to send our traffic to our pod after it's become ready. And say we're talking to a Kubernetes service, for example. That Kubernetes service, like a cluster IP, isn't able to route traffic to its backing pods until the pod becomes ready. That's the only time when an endpoint gets populated. So even if we did some clever trick to hack around readiness, we'd still be blocked on this, right? Like we're not going to be able to talk to our pods directly. So, well, we might have to talk to our pods directly if we want to get around that. So if we step back a little bit, we can take this holistic view and realize that there's this concept of not ready addresses that are in endpoints. So to explain a little bit of detail about how Kubernetes endpoints work and services, you have a service which is generally mapped to something like a deployment and more concretely a set of pods that service can route traffic to. It can only route traffic to those things when they're ready. That's the whole point. We're not going to send traffic to pods that aren't ready yet under normal conditions. Well, in addition to that, these endpoint objects which hold this set of addresses also have a block called not ready addresses, which are very useful for us because they're, as the name says, they're a set of pods that are not yet ready, but it's the networking information for them if you did want to talk to them. So what we can do is watch this, because in Activator, as I mentioned early on, we're watching the endpoint object to know when a pod becomes ready already. So we can watch that and say, oh, if there's a not ready address, and there's no ready addresses for this endpoint, go ahead and send traffic directly to those not ready addresses, or at least attempt to. Perform our own probing, essentially, for when that pod becomes ready and just bypass readiness altogether from a Kubernetes standpoint. So it has the nice perk of it fixes this minor data plane delay that we were seeing before. It also completely bypasses readiness in Kubernetes. Some downsides to this approach, though, end up being that we're doing our own load balancing at that point, right? You know, we're an activator deciding, hey, here's a set of IP addresses we can talk to. That logic ends up having to live in our activator if we go with this. One upside, though, or way to mitigate that problem, we're only watching for not ready addresses. As soon as we see a service become ready, what we can do is always send traffic there and do normal load balancing. And so basically, we're limiting this to the cold start case, which is essentially a load balancing with a backend size of 1. And very simple algorithm. And the only a bigger issue is that mesh networking poses a big problem here for trying to directly route to pod IPs. Because we know how, say, Istio works, or any of these mesh networking technologies, generally they firewall off the application and make sure that you're going through the client-side load balancing to do things like MTLS. That doesn't work if the pods you're talking to are not yet ready, because your client-side load balancing algorithm will not allow you to talk to them at that point. So we have to special case that. But that being said, this isn't not yet merged code yet, but I was able to hack together a prototype of this working. And what we can see is we're able to get request responses that actually happen before our pod becomes ready. So we're able to get a response from a not ready pod and also bypass data plane delay entirely for Istio. It ends up being a pretty neat hack if you can get this working. And in addition to the small time savings, what's really nice here is that any type of data plane delay that happens at scale, so say like you're running large Istio clusters, which may take longer to configure on pod startup, that is bypassed entirely with this approach. And roughly, this is where we're at today. Most of the low-hanging fruit has gone out, and we're at about 2 seconds of cold start time. And there's some unmerged code, and there's still some to do, but this is essentially where we've hit the wall of now we need to start looking to more difficult things, such as kubelet performance enhancements, which we've begun doing. Slight pitch for help upstream there. But that being said, we also have a slightly unrelated thing that's it's not going to affect our 2-second cold start performance out of the box, but if you've used Knative at scale, which not many have, one thing you end up noticing is that Kubernetes control plane performance ends up being highly variable at scale. I think this was mentioned in the previous talk as well about SLOs. Many of the SLOs are dictated about a cluster not necessarily being under high load. When your Kubernetes cluster becomes under high load, the Kubernetes control plane latency specifically is highly variable. And what I'm showing on this slide over here is on the left, this is the time before we see a pod start creating. So what I did here is I'm just doing 10 cold starts in parallel, which is a fairly small number, and we already see about a second worth of cold start, second time before the Kubernetes control plane begins starting a pod. As that number ramps up, that becomes significant. So as mentioned, the Kubernetes control plane performance is highly variable, and more importantly, many of the components, such as the replication controller, deployment controller, things like that, are not easy to really scale out. You know, you can do HA and things like that, but running multi-master, that is not a thing that they were really designed to do. And it's sort of an inherent design flaw, I would almost say, of this reconciler pattern. And it's not so much a flaw as a trade-off decision that was made for consistency over latency. It gets you reasonable throughput through things like batch processing, but latency isn't one of the upsides of this design. And so what we're looking at doing next, and we've done a fair bit of design work on, is actually bypassing this Kubernetes control plane. The idea being we can run the activator as a daemon set on Kubernetes. So when requests come in, we'll be able to send them directly to the activator on one of the nodes, which can then do local scheduling. This is done because if you know how scheduling Kubernetes works, there's a node name that gets written into a pod, and that's what tells kubelet that it should start looking at that pod definition and run it locally. Well, as a user, you can just write a pod definition with that node name already populated, which bypasses scheduling in Kubernetes entirely. So what we're going to do, or what we're hoping to do, is run activators as a daemon set on every node, locally schedule pods to that same node when requests come in, which bypasses most of the Kubernetes control plane. Notably, this doesn't bypass kubelet. So things like sidecar injection, admission controllers, et cetera, still work. But the reason this ends up being okay is because kubelet, unlike most of the Kubernetes control plane, is sharded and scaled out by node. Essentially, every kubelet is only looking for keys with its own node name, so it has very different scaling characteristics than the rest of the Kubernetes control plane. The end result being we can bypass this control plane variability for the most part and rely on the parts that do scale out. One downside, though, is if you notice, we're local scheduling to wherever requests come in. That means if essentially a load balancer is responsible for making scheduling decisions of where pods get placed. And so we have some design we've worked out, but essentially you have to be able to give hints to your load balancer to say, here are the places you should schedule requests for this certain application if they come in ahead of time. Because your load balancer isn't really something you can generally put a whole scheduler into and hack up a complex scheduling logic for. So you need to do ahead of time placement. Unfortunately, I don't have data on this. We did a little bit of prototyping a while ago. Just a very simple, run an activator as a daemon set, schedule a pod locally, and the results were fairly promising. But this is very forward-looking work. It's something that we're hoping to do over the next 2 cycles in Knative. So you have to stay tuned for that. And then lastly, I just want to give a pitch for coming and working with us. There's a whole lot of work to be done. And as I said, I was hoping to kind of catalog over the different components of Knative, the different tricks that we've found over the past 6 months for how we can work around some of these base performance characteristics of Kubernetes. Hopefully, you all can use them in your applications if they're useful. But if not, please come help us out. And this website up here, knative.dev, is where you can find all of our contact information if you have comments or would like to join. Any questions? And thanks. Hey.
Hey. Just real briefly, what are some of the performance work? What is some of the performance work in kubelet that you're looking for?
Some of the performance what?
The performance improvements in kubelet that you're looking for.
Yeah, what are the performance improvements in kubelet we're looking for? So one of the things, I've done some initial analysis on what we can do with kubelet, and we've realized that actually when those CRI container run calls are made, they actually happen in sequence, not in parallel. Just a straight, so like every one of those calls takes about 0.4 seconds, depending on the back end. And so the number of containers you have actually affects how long startup takes. So that was a sort of no-brainer. Another thing we've also noticed is that between CRI sandbox create and those initial container run calls, it seems like there must be some type of polling that's going on. And it makes sense when you look at the CRI API, there's no way to say, okay, CRI sandbox created, but the async processes about like when does an IP actually get realized in that sandbox, when does the V actually get attached into that C group. There's no back reporting interface. You just say, hey, sandbox create, and your CRI driver goes, okay, cool, I'm going to do that at some point. And then I think kubelet essentially polls for status of that. So some type of edge-triggered API there would be very helpful.
In this work, you assume that the node that is going to run the pod already downloaded the image, right? Because that's another time that can be like very long.
Yep. Yeah, so the question's about whether or not images are cached on the node already when you go to start an application. We've built in a caching sort of cop-out into Knative where it's like a CRD saying like, oh, here's the images you want cached, and then we assume somebody can write a controller that can say, oh, if this cache CRD has this image populated, you'll force it on every node. For my testing, I just manually push the images on there and bypass it. But we sort of just copped out and said, look, if you want it, you can write a controller for doing your own caching.
Have you considered keeping some running pods and they're not activated? Because this could also help if your actual application startup time is significant.
Yeah, the question is about whether, essentially, don't cold start, don't scale to zero, right? And we found it's really user specific. Some users are all about the cost savings. Maybe they have a model where they have tons of applications that are rarely used, and some people are definitely like, yes, give me that switch to never cold start. So we have the flag, but it's definitely not a thing we can just say, don't ever do.
So it's pretty interesting, but how will it work when you scale up? Meaning you start the first pod and it's working, but you're working around the load balancer, or at least the service load balancer. How will you make that work when you scale up to multiple pods, when you have lots of requests?
You're talking about with the daemon setup? How would you do it with lots of nodes?
Yeah, or at least, with the direct request forwarding too.
Sorry, I couldn't really understand.
Like when you're doing direct request forwarding.
This one? This was the last one.
Yeah, the one before. Basically, when you're directly forwarding the request to the pod instead of the service IP.
Oh, I know what you're talking about.
How will you scale up then?
How would it scale up? So the idea is the autoscaler is still in control of how many pods are running. It's setting the replica count on the deployments. And what the activator is doing is there's sort of two phases of that lifecycle. The activator is watching for whether there's any ready addresses in addition to not ready addresses. If it sees one of those, it's going to go normally through the cluster IP because that should work. And that kind of prevents us from getting this case of actually having to implement a real load balancer in the autoscaler or in the activator. Then the other component is when your application scales up, we do ask your ingress controller to redirect traffic to the service rather than the activator at all. So requests when your application are running are supposed to go directly to the pods themselves. But there's always a little window there because that's an async process. So.
Thank you for your talk. I have a question. I didn't get really, did you write your own scheduler? Because Kubernetes supports custom scheduler. Or you just bypass it at all? Just set node label and that's it?
Yeah. So like I said, we've only prototyped this. The design we've come up with so far is you're essentially deferring to the load balancer to do scheduling, which is a horrible scheduling algorithm but all it's doing is saying whichever node the request comes into, that is where the pod is going to end up getting scheduled. Our plan is roughly to do what's called subsetting. So we're going to ahead of time say, look, maybe these 2 nodes or these 3 nodes are the only nodes that should serve requests for this application. The idea being then you're limiting the path of if a request comes into one node, then a second request comes in, you're not going to pay cold start every single time. It's just ahead of time placement, essentially.
Any other questions?
Great, thank you.